Hello, I'm Anna Mackay, and this video will be about testing claims about mu within confidence intervals. So we've got two scenarios here, and we're asking, has there been a change in the weight of 5 and 20-cent coins over the past 47 years? So in 1970, the mean weight of 5-cent coins was 2.837 grams, and the mean weight of 20-cent coins was 11.313 grams. In 2017, a sample of 80 was collected for the 5-cent coins, and our mean of those 80 coins was 2.836. So having a look, yes, they're slightly different, but is it enough to say there's been a change overall? We're going to assume the standard deviation will remain constant in both sets. Likewise with the 20-cent coins, yes, you can see a difference in the means, but is it enough to say there's been a change or not? All right, so looking at the 5-cent coins, this is trying to really get your head around what a confidence interval is with your sample versus your population mean. So our one sample of 2.836, that gave a mean of that. Try and visualize that. So that is one sample. If we conducted this many times, collecting 80 coins, you'd get lots of different means somewhere between all of these numbers, with varying ranges of decimal places. So here's the previous mean, and this is our sample here. Okay, they're different, yes, but how far away is it? So it's smaller. Is it enough to say that it's a reasonable sample or it's an outlier? So as we know, when you collect samples every time, you're not always going to get exactly the population mean. The central limit theorem tells us it will be approximately the same. So is it a reasonable difference? Alright, so if no, according to the central limit theorem, we would expect no change and therefore that they would be exactly the same. And here is our previous mean, our 2.837. And our new mean, 2.836, lies here. And we know that a 95% confidence interval is nearly 2 standard deviations away from that true mean. And so looking at our graph here, you can see it's not quite that. So it doesn't look like there's going to be evidence. Working out a confidence interval, using your calculator, your confidence level of 0.95, standard deviation, 0.007, etc., etc., you end up with a confidence interval ranging between this, and you have to go back and assess, was that previous mean in the region? So 2.837, it lies at the upper end, but that doesn't mean it's any more likely, but it's still within range. So what we say is, therefore, there's not enough evidence to suggest a change in the mean weights of 5-cent coins. So perhaps just that sample had a few coins that had slightly below average weight, and that's why it's not exactly on that previous mean. Now, it's important to note that just because 2.837 is towards the upper end of the confidence interval, so it's closer to this number, it does not imply that the true population mean of the 5-cent coins is above X bar. Every value within the confidence interval is equally likely. So you can't say that the true mean is closer to one number or the other number. All of them are equally likely. So the 20-cent coins now. Our previous mean was this, 11.313 grams. And then the sample that we took 47 years later had a mean of 11.320. So if you put your mean there and spread them all out, this is where our sample would lie. So what we've got here are lots of samples, all these little X's, lots of samples with 40 coins in them, taking the average, and here's our one sample. So we're looking at the mean of the means here. Okay, so is that an outlier, or is it still a reasonable distance away? So according to the central limit theorem, we can assume the means are going to be the same, and then our standard deviation divided by the square root of n would give us this standard deviation, and if you calculate that, this is where our new sample sits. And we know that we need to get it within 2 standard deviations to be reasonable and to imply no change. That's too far away. So 95% of sample means would lie within 1.96 standard deviations either side of mu, and ours does not. So that means out of, well, I'll tell you on the next slide here, So it suggests a change or an increase in the mean weight of 20-cent coins. And it's either a very rare event occurred in our sample of 40 or the original mean has changed. So what I mean by that is to get that average of 11.32 grams, imagine all the coins in there. You had 40 coins. Each of their weights would have to each be above average to end up with the whole average being that far away from the previous mean. So that is possible, or it implies that that is an accurate sample of the current coins in circulation to imply that the mean perhaps has increased, the mean weight has increased on those coins. So the confidence interval that you end up calculating ends up being this, and then you have to go back and assess your previous mean, mu. 11.313, you can see is completely below this confidence interval, so it's not in the range. But that we have to bear this in mind. That sample that we took of 40 coins, where we got a weight of 11.32, we cannot say that that is the new mu, the new population mean, since it was only one sample taken. That could be at the top or the bottom end of the range. And visualize this. So if our new population mean, our new mu, was here, and 11.32 could actually be on the lower end. So they could actually be a sample of lighter coins overall. So our population mean could be higher, or 11.32 could be at the upper end in comparison to what the true mean would be. So it could be here. So taking those two portions of the confidence interval, the center of that is 11.32, and so we've got this endpoint and this endpoint, and if you work out the areas of those and flip them, that's how you get the equivalent of the 95% confidence interval. So it's very likely that that population mean will be in here. Okay, so just summarizing some of this, to test a claim, just see if the population mean could take a particular value, we construct a confidence interval, and that is about the true population mean mu. And so the two scenarios that could happen, if mu does not lie within the confidence interval, as with the 20-cent coin, it implies a change has occurred. Not definitive, 95 out of 100 samples is what we're looking at, so it could be one of those 5 samples that was rare, or perhaps 95 of them are telling the truth, and so that's implying a change. Or, oops, missing an I there, if mu lies within the confidence interval, there's not sufficient evidence to suggest a change in mu, as we had with the 5-cent coin. So they'll be a little bit different, but not enough to suggest a significant change. Confidence intervals cannot be used to make definitive statements about whether a claim is true or false. Their purpose is to give a guide, a few typos here, to whether a claim is reasonable. Remember, if it's a 95% confidence interval, that means that on average, 95 out of 100 samples will contain that mu, but 5 will not. So you can never be 100% certain about mu. So if those 20-cent coins imply that there is a new mu, how could you work that out? You would have to weigh every single 20-cent coin in circulation to find out what the true mean is. Okay, so moving on to 2 quick examples here. Educators have previously surveyed a group of students, and their scores on a standard test had a mean of 60 and a standard deviation of 10. I like to, when I'm doing these types of questions, extract out those numbers as I go. So I know we're going to do a confidence interval at some point, and the values that you need in that are these. So sometimes it's quite handy to write them as you find them. Okay, so the previous mean was 60. So I'm going to write that as a separate one, 60, and a standard deviation of 10. So we assume they remain constant. Later, they wish to determine if there has been any change up or down in the mean, assuming the standard deviation remains the same. A sample of 50 students, there you go, there's your N, 50 students, gives a mean of 62.5. That's your X bar. use a 95% confidence interval, so 0.95, to determine if a significant change has occurred. So just as a quick observation, 60 is what it used to be, 62.5 is what it is now. So it looks like it may have increased, but we have to see if this confidence interval contains this mu or sits completely above. When you work that out, you get 59.73 on one end and 65.27 on the other. Mu is in the middle, not x bar. And there we go. So where is 60 in comparison to this? It's within. So we cannot definitively say that a change has occurred. So how to sum this up? We cannot say or confirm that a change has occurred. Why? As 60 is within the confidence interval. You can abbreviate that to CI. So although that has increased, it's not far away enough, as in 1.96 standard deviations away from that original mu, the previous mu, to imply a change. And our second example, a large group of school children were previously tested on their fitness levels by timing them over a 50-metre run. The mean was 12.0 seconds, that's your old mu, and the standard deviation was 2 seconds. After an intense fitness program, 40, there's your N, of the children are tested again. The mean of this group is 11.3 seconds, so X bar. So that's lower, so that could imply that this fitness program, they're getting faster, they're getting better, and it has had an effect. Assuming that the standard deviation remains the same, construct a 95% confidence interval to decide if the fitness levels have improved. So please write out the setting out each time, these values, 2 seconds for a standard deviation, 12.0 and 40. And you come up with a confidence interval of 10.68, mu in the middle, and 11.92. And you always use that to compare it to the previous mu of 12. Where is 12 in comparison here? Aha, it's outside of the confidence interval. So you can either say the previous mean is completely above, or the confidence interval lies completely below, and so this implies a change. So the question asks us to decide if the fitness levels have improved. So since the previous mean mu of 12 lies above the confidence interval, this implies fitness levels have improved. Have improved. Okay, just thinking about what could have happened here, remember, if we did 100 samples, in 95 of them, this is implying that whatever the new mean is, it will be in there, but in perhaps 5 it won't be, approximately 5. So this one sample could just have students that have really had a positive impact from this fitness program or are really fast. And so the sample that they generate implies that everybody else is faster now, but that might not be the case. But that's why it's a 95% confidence interval, and we don't have to be 100% certain. And then the last part here is what would happen if the mean of the sample had been 11.3 seconds instead of 11. What did we have? God, drat. I meant to write 11.4 there. Change that to 11.4, please. So just slightly different. Drat. Do you know what I've done back up here? Here, where I wrote 12, that was supposed to be 11.3. The confidence interval I've given you matches 11.3, doesn't match 12. We're all human, we make mistakes. Sorry about that. X bar is 11.4 and N is 40. And the confidence interval for that gives us, 10.78 greater than or equal to mu between 12.02. So now where is 12? 12 is within this confidence interval. So reading what the question asks us, would the conclusion be the same or different, and explain. So this would imply that the fitness program has not improved levels, because this implies, feel free to speed this up, that fitness levels have not improved. Have a think of why. Have not improved because you always have to go back to that original mu because mu is equal to 12 is within the confidence interval. It would have to lie completely, the confidence interval will have to lie completely below to imply that a change has occurred. Okay, that's in this video. The next one in the series will be called sample proportions. Thank you.